Welcome! In the first tutorial, we built the Smart Switch 1.0. Today, we will upgrade it to version 1.1 by adding a light intensity sensor for real-time light monitoring. For those who are watching us for the first time, this video is a part of a longer series where we keep improving our smart light switch. And in this episode, we will focus only on the changes needed to make the device work with a light intensity sensor. I will not repeat the software and hardware setup since that's already covered in the first tutorial. You can find the link in the description. Please keep in mind that in this tutorial I will show you how to make a single light switch with the one light intensity sensor that controls one bulb. In another tutorial you will find out how to build a double switch with two sensors to control two bulbs. So make sure you don't miss next tutorials by liking this video and subscribing to my channel. Let's get started. Visit my GitHub repository using the link in the description. There you will find everything for this project plus extra tips and recommendations. In this video, we will open the folder for version 1.1 and I will also show previous version 1.0 to highlight the changes. The sketches show exactly how all the components should be connected in order for our device to work. When we compare the new sketch on the left with the one from our previous tutorial on the right, we can see that the only change is the addition of a BH7050 light intensity sensor. The BH7050 is a 16-bit ambient light sensor that communicates over A2C and outputs illuminance in lux, which is a unit of a light intensity. It measures from 1 to 65,535 lux and can be used in many projects. For example, detecting day and night, adjusting LED brightness, or checking if a light is on. For more technical details, see my GitHub repository. The yellow cable connects the SDA pin to D3 and the green cable connects the SCL pin to D4 on our microcontroller. SDA stands for Serial Data Line and this is the line that carries the data bits between the microcontroller and BH7050. The SCL stands for Serial Clock Line, so this is the signal that controls the timing of data transfer. We power the sensor using the orange and brown cables. As usual, we can check if the signal is being transmitted by observing whether the LED blinks each time a signal is generated from our webpage, so each time we click a button on or off in our application. I'm also using 4 long wires, about 4 meters each, since that's the distance between my switch and the overhead lamp. The sensor will be mounted next to the bulb in that lamp. These cables were derived without pre-installed connectors, so I used male pin rasters and BLS connectors to create the connectors myself. Okay, let's connect BH7050 to our device. hardware part is ready. Now let's move on to the software. Let's take a look at what has changed compared to the code from the previous tutorial. We add BH7050 library that simply lets us use our sensor, and the wire library, which is required to communicate with the sensor using A2C. Next, we define the pins for communication with the sensor. Pin D3 will be the SDA line, and pin D4 will be the SCL line. Then we create the light sensor object so we can read the values from it later. We also update the title on our web page to reflect the current version 1.1 of this project. We add a new visual effect, a light blue border around the on and off buttons. If the light in the room is on above 1000 lux, the on button will be highlighted. If it is off below 1000 lux, the off button will be highlighted instead. This is done using a CSS class called active. The threshold of 1000 lux is not random. I tested this in my room many times and discovered that around this value, the sensor correctly shows whether the light is on or off. What is more, it also works well during the day, even when the room is naturally bright. How do the buttons update? Every 5 seconds, our web page sends a request to the ESP to check the current light level. In JavaScript, we first get the button elements, then we create a function update light intensity that sends a request to the microcontroller. If lux is equal or greater than 1000, the on button gets the active highlight. If lux is less than 1000, the off button gets highlighted instead. Finally, we send the request and repeat it every 5 seconds, so 5000 milliseconds. The request is asynchronous, which means it works in the background, so the page stays interactive. This is really important because while the page is waiting for a response from the sensor, you can still click buttons, so turn the light on and off. To make this work, we add a new function that reads the current light level and sends it back as plain text. Then the web page client uses parse float function to convert it into a number. Finally, in the setup function, we start A2C communication. We initialize the sensor and register the new endpoint / get light intensity on the web server. So if you go to this address in your browser /get light intensity, you will see the current light level in lux. If you're having trouble understanding the logic of our code, I highly recommend reading carefully comments included in the source code or watching the first video in the series, where I explain the rest of the code step by step in detail, or familiarizing yourself with the basics of HTML, CSS, JavaScript, and C++. And this is all. Now let's copy the ready code from the GitHub repository and create a new sketch in the Arduino Cloud. Make sure you have the Cloud Arduino agent plugin installed, since it enables serial communication between your board and the Arduino Cloud accessed through your web browser. After logging in, create a new sketch, paste the code, plug the microcontroller into your computer via USB, and choose version 1, since version 3 that we are using is not listed, but 1 should work. Now upload the ready program to our microcontroller. I will double the speed of the video now. It's time to test our device. The boards are covered with double-sided tape, so I'm using them and a drop of super glue to place the servo. We carefully tape the hanging cables to the wall to avoid any damage. It's not the most convenient setup, but since this is just a prototype, we only need a temporary installation for testing. In the final design, I would connect them into one white cable. The sensor is also mounted with a tape close to the bulb in our overhead lamp. Make sure not to cover the sensor itself. Now power on the switch, find your ESP Wi-Fi, enter the password you set, and visit the web page to test it. You can add a web page shortcut to your phone's home screen for quick access. You can see that now, according to the sensor, the light is off. We turn on the light and wait for the button highlights in the app to change accordingly, based on the sensor reading. Remember, you have different power options, and there are also versions without LED or breadboard. Thanks for watching this tutorial. I hope you found it useful. I really appreciate you joining me in exploring this fascinating world of technology. If you build this device yourself, feel free to share your experience in the comments or tag me. I'd love to see your results and leave a like or comment. See you in the next tutorial, where we will take this project further and make it more convenient by moving away from access point mode.